Hi learners. Welcome to my video. Today we will learn how group theory came into our literature. So make sure you watch the whole video and keep notes of it during the lecture. So, let's start. We all know what sets are? So at first, we will discuss the definition of Cartesian product of two sets. Where A belongs to the set A and B belongs to the set B. The Cartesian product of the sets A and B is a set having elements in the form of ordered pairs as shown. Where two such ordered pairs are equal if their corresponding elements are equal as shown. Also keep in mind that A cross B is not equal to B cross A. The ordered pair, which has same elements, is called diagonal of the product. Now we will discuss the binary relation. It is a relation between two sets, denoted by R. The ordered pair of A and B belongs to R, means that A is related to B under the relation R. If we are dealing with Cartesian product of two sets, then this relation is called binary relation. And if we are dealing with Cartesian product of three sets, then this relation is called ternary relation. At last, if we are dealing with Cartesian product of four sets, then this relation is called Quaternary Relation. A relation between the same sets is said to be an equivalence relation if the relation R holds following three axioms. First one is, for all A belong to A, there exists diagonal ordered pair in R, which is said to be reflexive property. Also we can say that for each A belongs to A, is related to A. Second one is, for all A, B belong to A, if the ordered pair of A and B belongs to R, then the ordered pair of B and A also belongs to R, which is said to be symmetric property. Also we can say that if A is related to B, then B is related to A. At last, if A is related to B, and B is related to C, then A is related to C, which is said to be transitive property. Now, we will discuss equivalence classes of elements of sets. Equivalence class of A belongs to A is the set of those elements of A, which are related to A, under an equivalence relation, R, on the set A. Next, we will discuss the definition of partition of set A. Partition of set A is a collection of subsets of the set A, such that all those subsets are disjoint, and their union is equal to the set A. Now, we will discuss that the distinct equivalence classes of an equivalence relation on set A gives us decomposition of the set A. At first, since R is an equivalence relation, so from reflexive property, A is related to A, which implies A belongs to its own equivalence class, so A belongs to the finite union of all equivalence classes of set A, which implies finite union of all the equivalence classes of set A is equal to the set A. Now to prove distinct equivalence classes of set A are disjoint. Suppose contrary that distinct equivalence classes of A and B are not disjoint. So, suppose X belongs to the intersection of those distinct equivalence classes, which implies X is an equivalence class of A and also an equivalence class of B, so we can say that X is related to A, and thus from symmetry, A is related to X. Similarly, we can say that X is related to B. Now transitivity implies that A is related to B. Now for any Y in the equivalence class of B implies that B is related to Y. Applying transitivity, we get A is related to Y, which implies Y is an equivalence class of A, but Y was in the equivalence class of B, so equivalence class of B is contained in equivalence class of A. Similarly, we can get equivalence class of A is contained in the equivalence class of B, which implies that both classes are not distinct, which is contradiction to our supposition. So we can say that distinct equivalence classes of a set are disjoint. So, this proves that distinct equivalence classes of a set give us a decomposition of that set. Now we will discuss the definition of a mapping or a function. Let f be a function mapped from a set S to a set T, such that for every S belongs to set S, there exists a unique T in set T, such that f of S is equal to T. Now, we will discuss the definition of on-to mapping, which is that for a mapping from S to T is on to if for each T in set T, there exists S in the set S, such that f of S is equal to T. Next we will discuss the definition of oneone mapping, which is a mapping from S to T, such that all distinct elements of set S have distinct images in set T. Next we have a mapping which is called bijective mapping if it is both onto and one. Next we will discuss the term composition of mappings. Consider a mapping F from a set A to set B, and a mapping G from a set B to set C. Then composition mapping of both F and G is mapped from set A to C, as we first apply F and then G to get G of F. If we make a set of all bijective mappings from a set S to itself, then we see that this set of bijective mappings holds some properties. The mappings hold closure property and associative property under the operation of composition of mappings. Identity mapping lies in this set also, as this mapping is bijective. At last, since the inverse mapping for each bijective mapping exists, so inverse mapping for each bijective mapping exists in that set also. These four axioms lay foundations of group, which leads us to the end of our topic. In short, group theory is an evolution of basic set theory, mappings and sets with certain properties with respect to a specific binary operation. Learners, this is the end of our video. Thanks for watching. Bye.